Good morning to everyone. I, Dr. Manoj Kumar, Assistant Professor in the Department of Science and Technology, IIMT Group of College, Greater Noida. Today I am going to take lecture on the topic Fourier series and its application. This topic is very important. Therefore, I thought this should be covered in this session. The outline of my lecture is first, motivation of studying Fourier series. Second is preliminaries. Third is Fourier series. Fourth is application of Fourier series. Last but not least, fifth one is references. Next slide comes with motivation of studying Fourier series. Why we are studying Fourier series? What are the features behind the Fourier series? Fourier series is widely used in many branches of science and engineering. It is most powerful tool to solve the ordinary differential equation as well as partial differential equations with periodic function appearing as non-homogeneous terms, particularly to obtain solution to the partial differential equation problems. For example, Laplace equations, wave equations, heat equations, etc. We should need to know how to expand a function into a trigonometric series. Since each terms of the trigonometric series is periodic, it is clear that if you are going to expand a function in trigonometric series, then the given function should must be periodic. Now you can able to say here Fourier series and infinite series expansion of a periodic function in terms of sine and cosine functions. Now in this slide, we will discuss about the sequence and series. Sequence is nothing but an arrangement of any objects in a particular order followed by subrule. For example, sequence of natural number. Second is sequence of even number, sequence of order, sequence of odd number. In these all example, what you find? There is some pattern which is followed by some rule. Therefore, you are able to say this is sequence. Now, series. If the terms of the sequence are added, then the expression obtained is called series. Now we will discuss here infinite series. Let xk be a given sequence of real numbers, then an expression of the form given in equation 1, summation running from k equal to 0 to infinity xk equal to x naught plus x1 plus x2 and so on is called an infinite series. Now, the nth partial sum of the series given in 1 is given by equation 2. In this expression, what you find? We have fixed the value of k up to n. Therefore, you are saying the series 2 is called finite series because we have fixed the value of k up to n. Now here we will study convergence of infinite series. If the sequence of partial sum Sn of the infinite series 1 has the limit s, then the series converges to the limit s and it is denoted by limit n tends to infinity Sn equal to s. It means that Sn converges to s as n tends to infinity. If the sequence of partial sum Sn of the infinite series 1 tends to infinity or minus infinity, then the series is said to be divergent or oscillator. Now here we will begin definition of periodic function. Before going to the definition of periodic function, we will discuss something that is when you have a function and you are thinking for expanding that function into trigonometric series, and the terms of each and every terms of trigonometric series is periodic. Therefore, the expense the function which you are looking for expanding that should be periodic. So, what is the meaning of periodic? What is the meaning of periodicity? Something that repeats after a certain interval of time. We can take some real life example. Magazine, newspaper, journals. These are all example of periodic because it comes out to be daily, weekly, monthly, quarterly, annually. Another example will be a clock. Next is pendulum. These all things repeat itself after a certain interval time. Here in the case of mathematics, what you see periodic function. A function f of x is said to be have a period p for every x, f of x plus p equal to f of x. It means that you are adding any constant p in x, you will getting same result where p is a positive number. The smallest value of p greater than 0 is called the fundamental period of the function f of x. If f of x has period p, then 2p, 3p, 4p, 5p, and so on are also be the period of the given function f of x. Thus, for any integer n equal to 1, 2, 3, and so on, we are able to write f of x plus n into p equal to f of x for every x. Now here we will discuss some examples of the periodic function. Sin x and cos x have period 2 pi. How can you say sin x and cos x have period 2 pi? If you visualize the graph of if you will visualize the graph of sin x and cos x, you will find that it repeat after certain interval. Means value of sin x repeats after interval of 2 pi. So sin x has period 2 pi, 4 pi, 6 pi, 8 pi, and so on. Since sin x plus 2 pi, sin x plus 4 pi, sin x plus 6 pi, and so on is equal to sin x. Here, the least period of the sin x is 2 pi. Therefore, you are able to say 2 pi is the smallest period of sin x. Similarly, for the case of cos x. Now, how can you find the period of sin squared x and cos squared x? Both the functions have period pi. How can you find? By just writing the formula of sin squared x. What is the formula of sin squared x is? 1 minus cos 2x upon 2. And then individually, if you will apply period of the function, then finally you will get period pi. Similarly, cos square x. In third case, sin cube of x and cos cube of x have period 2 pi. How? Similarly, you will use the formula of sin cube x and cos cube x, we will obtain period 2 pi. In fourth case, sin nx and cos nx have period 2 pi upon n. Means when some n will be multiplied by x, that coefficient will come in denominator upon the period of sin x. Next is tan x and cot x have period pi. If you visualize the graph of tan x, then what will you find? Uh, at the point minus pi by 2, it goes to the minus infinity, and plus pi by 2, it goes to the plus infinity. So in that interval, it repeats itself on the real line. So the period of tan x and cot x is pi. Now here we will discuss one important thing is that the period of constant function is any positive number. How can you say period of constant function is any positive number? Firstly, we will discuss what is constant function. Constant function is f of x equal to c. If you give any value of x, you always get the constant c. Now, if you add any positive number, any number, f of x plus p, you will get constant c. If you add again f of x plus 2p, we again get c constant, same constant, and so on. Therefore, you are able to say the period of constant function is any positive. And one thing is that, moreover, one thing is that there is no fundamental period of the constant function. How? Because you are not able to find the smallest number for which f of x plus p equal to c. Because some student will say 0.1 is the smallest number. Then f of x plus 0.1 will give you constant. But after some time, other student will say, I have a number lesser than 0.1. That number will be 0.001. In 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 this case also, f of x plus 0.01 gives you constant. Some other student will come and say, I have also a small number lesser than this. That will be 0.0001. So in this case, what you see, you are not able to find the smallest number. You are able to say number, a smaller number, but it is very tough and hard to say the smallest one. Therefore, you are able to say here, there is no fundamental period of the constant function. Now we will discuss properties of periodic function. The first property is periodicity is a domain-based property. Second, a function may or may not have fundamental period. We have already discussed that the constant function have no fundamental period. F of x equal to c for all x belonging to real number. Third point is if f of x and g of x have period p, then the function combined function h of x equal to a into f of x plus b into g of x has also the period p, where a and b are constants. Next property is if the function f1 of x, f2 of x, f3 of x, and so on have periodic function with period p1, p2, p3, and so on respectively, then their combination of functions have also period equal to LCM of p1, p2, p3, and so on. And the last property is if the function f of x is a periodic function with period p, then the period of this expression, which we are able to see here, a plus f of b into x plus c have period p upon modulus of b. Now, here we will discuss the definition of Fourier series. This is the main definition of our lecture, that let f of x be defined in the interval minus pi to pi and determined outside of this interval by assuming the function is periodic of period 2 pi. That is f of x plus 2 pi equal to f of x. Then the Fourier series or the Fourier expansion corresponding to the function f of x is defined by f of x equivalent to a naught upon 2 plus summation running from n equal to 0 to infinity an cos nx plus bn sin nx, where the Fourier coefficient a naught, an, and bn are called Fourier coefficients. A naught is given by 1 upon pi integration running from minus pi to pi f of x dx. An equal to 1 upon pi integration running from minus pi to pi f of x cos nx dx, and bn equal to 1 upon pi integration running from minus pi to pi f of x sin nx dx. These coefficients are also known as Euler formula. Now here we will discuss one thing. The expansion of functions in series of sine and cosine is developed by a French mathematician, Joseph Fourier. And by the help of Maclaurin theorem, you are able to expand the function f of x in terms of power of x, provided that function should be continuous and its derivative should also be continuous. Then you are able to expand. But the problem arises when the function and its derivative is not continuous. In that case, what will happen? By the help of Fourier series, we can expand both type of function under certain conditions as an infinite series of sine and cosine. Conjugate Fourier series. The conjugate series of the Fourier series is given by equation 5, and it is said to be conjugate Fourier series. Now in this slide, we will discuss convergence of Fourier series. F of x equivalent to a naught upon 2 plus summation running from n equal to 0 to infinity an cos xn plus bn sin nx. Now here, this equation 6, the series 6, is only series which correspond to f of x. If you are not aware here, you have no any knowledge that this series right hand side of the equation 6 will converge or not. Even if it will be convergent, whether it converges to f of x, there is question mark. This problem of convergence was examined by Dirichlet, who developed the condition of convergence of Fourier series. Now in the next slide, we will discuss the Dirichlet condition, which will be responsible for the convergence of Fourier series. This Dirichlet condition is the sufficient condition for the uniform convergence of Fourier series are called Dirichlet conditions. All the functions that normally arises in science and engineering satisfy these conditions. Suppose that first condition is f of x is defined and single valued except possibly at a finite number of points in the interval minus pi to pi. Second one is this: f of x is periodic with period 2 pi. Third one is f of x and its derivative are piecewise continuous in the interval minus pi to pi. Then the series 6 with its coefficients convergent to converge it to f of x, in which case if x is a point of continuity. In the second case B, if x is a point of discontinuity, then what will happen? This will converge it to the mean value of the left hand side, left hand limit, and the right hand limit. The condition 1, 2, and 3 imposed on function f of x are the sufficient condition but not necessary condition. That is, if the conditions are satisfied, then the convergent is guaranteed. However, if they are not satisfied, then the series may or may not converge. The above conditions are generally satisfied in the problem of science and engineering only. These are at present, there are no known sufficient and necessary conditions for the convergence of the Fourier series. It is of great interest that the continuity of f of x does not alone ensure the convergence of the Fourier series. Now here on, we will discuss even function and odd function. The first definition is even function. What is even function? A function is said to be even function if it satisfies this property f of minus x equal to f of x. For example, x squared, x to the power 4, comma, 2 into x to the power 6 minus 4x squared plus 5 cos x, etc. are the example of even functions. Second definition, odd function. A function is said to be an odd function if it satisfies f of minus x equal to minus times f of x. For example, f of x equal to x, f of x equal to x cubed, f of x equal to 2x to the power 5 minus 3x squared plus ax plus 1 sin x tan 3x are the example of odd functions. Now here we will discuss the product of two odd function is even function. The product of even and odd function is odd function, and the product of two even function is even functions. Can you able to say a function? There may be a function that will be neither even function nor odd function. Is there any example? There is one example in mind that f of x equal to x minus x. This function is neither even function nor odd function. So we can check this example by the conditions. Now in this slide we will discuss Fourier cosine series and sine series. Fourier cosine series. The Fourier series of an even function of the period 2 pi is a Fourier cosine series. In this case, we have even function, and we will, if you will extend that even function, you will get equation 7. In this equation 7, what you see, there is only constant term and cosine term are here. There is no any term of sine. Where a naught you will get by the given formula, and an you will get by this formula 1 upon integration running from minus pi to pi f of x cos n x dx, and this will be even function. Then we will take 2 upon pi integration running from 0 to pi f of x cos n x dx. Second is Fourier sine series. The Fourier series of an even function of period 2 pi is a Fourier sine series. This expression is Fourier sine series. What you will find in this expression? There is only term of sine term only. There is no constant term and no any other cosine terms. And this Bn you can find by applying this formula, Bn equal to 1 upon pi integration running from minus pi to pi f of x sin ns dx. Next slide is half range Fourier series. If the function f of x is defined over half the range, that is 0 to pi, instead of the full range minus pi to pi, it may be expanded in a series of cosine term only and the sine term only. The series produced is then called half range Fourier series. Sometimes there is requirement of expanding the function in half range series. Half range means 0 to pi instead of full range Fourier series minus pi to pi. In that case, what will happen? The function is immaterial in the outside of the interval 0 to pi. But here we have two choices, arbitrary choice that in the first case, you can assume the function is even function. Means you will expand the function by considering that function should be symmetric about the y-axis. Then you will get cosine series. In that case, sine there will be no any sine term present in the expansion of the function f of x. Here it is even Fourier cosine series. So you are able to say an equal to 2 upon pi integration running from 0 to pi f of x cos n x dx, and a naught equal to 2 upon pi integration running from 0 to pi f of x dx, and there is no any term of sine because bn is 0, because we have expand that function symmetric about the y-axis. That is, you have considered the function is even function. But in second case, what will happen? You are outside of the range 0 to pi, we have considered that function is odd function. It means that you have constructed or drawn a function outside of the interval 0 to pi, that is in the interval minus pi to pi. It is symmetric about the origin. That is, the function is odd function in the interval minus pi to pi. In that case, what will happen? You will get value of bn equal to 2 upon pi integration running from 0 to pi f of x sin x nx dx, and n equal to 0 because there is no any cosine term and constant term in the value of bn. Now, here is one example, f of x equal to x in the interval 0 to pi. Here we have interval half range 0 to pi instead of minus pi to pi. So in this case, you will find Fourier cosine series and sine series. So in the for finding the cosine series, what you will do? You will draw a function symmetric about y-axis, then you will get even function. And after expanding that function, you will get only cosine series, cosine term. There will be no any term of sine because the function is even function. In the second case, what you will do? If you are looking for a sine series, you will do what? That you will draw a function considering odd function, and you will draw like symmetric about the origin. In that case, the obtained function will be odd function, and the expansion will contain only sine series only. There will no any term of cosine and constant term. The next slide is application of Fourier series. There are numerous applications of Fourier series to solution of boundary value problem. For example, first is heat flow, Laplace equation, and vibrating system. These are the application of Fourier series, which is very important point of application. Now, last is references. The first reference, the book having title Trigonometric Series, authored by A. Zugman, and second is book name is Advanced Engineering Mathematics, authored by Irvin Crazy. Third one is the name of the book is Higher Engineering Mathematics, authored by H.K. Das. Fourth is Engineering Mathematics, written by N.P. Bali and M. Goyal. And the fifth is name of the book is Fourier Analysis with Application to Boundary Vary Problems, written by M.R. Spiegel. Thank you everyone for attending the lecture. Thank you for your patience for listening to the lecture.